Let's talk about something that's all around us, but completely invisible. I'm talking about the hidden, complex infrastructure that powers our daily lives. The stuff we totally depend on but almost never think about. And we're going to start with one of the most basic, our water systems.
I mean, just think about it. Right now, right under our feet, there's this gigantic network of pipes and pumps and treatment plants, all working around the clock. These are these huge, silent systems just tirelessly delivering clean, safe water to millions of us. It's a constant, reliable flow that is honestly nothing short of a modern marvel.
But here's the question that keeps engineers up at night. What happens when a critical piece of that system, a part that might be 50, 60 years old, just breaks?
See, this is where a simple break turns into a full-blown crisis. For a lot of these older parts, there are no spares. The company that made it might not even exist anymore. You can't just go online and order a new one. There's no off-the-shelf solution. So when a part like this fails, the whole system is down, and there is no easy fix in sight.
So to really get a grip on this challenge, we're going to look at a real-world example. Let's zoom in on Northumbrian Water. They're a major utility company in the UK, and they're facing this exact problem, but on a massive, massive scale.
The scale of their operation is just staggering. Okay, get this. Northumbrian Water serves 2.7 million people. They supply over a gigaliter, that's a billion liters of fresh drinking water every single day. And all of this is managed by thousands of pieces of equipment, many of which were built way before the digital age.
And that brings us right to the heart of our story, the obsolescence crisis. This is what happens when the machines of today rely on parts from yesterday, parts that have, just run out of time.
And this is the star of our show. It might not look like much, but this broken belt pulley, it's a huge headache. It's a critical part from an essential machine, and it failed. And with no replacement handy, a vital public service is now at risk.
Now, let's put this one part in perspective. This isn't just a one-off problem. For Northumbrian Water, this is just one of over 15,000 parts that need to be fixed or replaced every single year. The scale of this is just immense.
And what happens if they try to get a part like this custom-made the old-fashioned way? Well, the lead time can be up to 40 weeks. That's almost 10 months of just waiting, while a critical system is completely offline.
And here's the bottom line. Every single day that piece of equipment is down can cost the company up to $2,000. Now you multiply that over weeks or even months, and you're looking at catastrophic costs and major service disruptions. It was crystal clear. They needed a new solution, fast.
And that solution came from a really innovative collaboration. It was all about bridging that gap between old-school heavy industry and cutting-edge high technology. Northumbrian Water decided to ask for a very different kind of help.
They teamed up with the advanced manufacturing specialists at Autodesk's Technology Center. So you've got this partnership that brings together deep, boots-on-the-ground knowledge of water infrastructure with some of the most advanced digital manufacturing tools on the planet. Now, the secret sauce here is a technology called hybrid manufacturing. It sounds super complex, but the idea is actually really elegant. It combines two totally opposite approaches in one single machine. Building material up, layer by layer, that's additive manufacturing, or what you'd call 3D printing, and then precisely carving material away, which is your traditional subtractive machining.
This slide really breaks it down perfectly. So the top path, that's traditional manufacturing. It's like starting with a big block of marble and just chipping away everything that isn't your statue. The bottom path is hybrid. It's more like using clay to build up the rough shape you need first, and then bringing in the sculpting tools for all those fine details. You waste way less material, and you get incredible flexibility.
So how did they actually apply this amazing tech to fix that busted pulley? Well, the process took it from a broken piece of junk metal to a fully functional part, one step at a time.
They followed what you could call a four-step resurrection process. It starts in the physical world, jumps over to the digital, and then comes right back to the physical. Scan, model, 3D print, and machine. Let's break that down.
First up, the scan. The team used a laser scanner to capture millions and millions of data points from the surface of that broken pulley. What this does is create a super accurate, but also really complex digital mesh. Think of it like a 3D photograph of the part, including all the damage. Next, the model. So engineers take that kind of messy scan data and use it like a blueprint to reverse engineer a perfect, clean 3D CAD model. This essentially creates a digital twin, a precise virtual copy of what the original, unbroken part is supposed to look like.
Step 3 is the 3D print. Okay, this is where the magic really happens. They take the original broken part and put it inside the hybrid machine. Then, guided by that perfect 3D model, the machine's additive head starts depositing new metal, layer by painstaking layer, directly onto the broken areas. It's literally unbreaking the part by adding back what was lost.
And finally, the machine phase. Inside the very same machine, the process flips from additive to subtractive. A precision milling tool comes in and carves away any tiny bit of excess material from those newly added sections, finishing the part to the exact, perfect dimensions it needs to be. The resurrection is complete.
So the process is incredibly cool, right? But what was the actual result? I mean, what did this new approach really achieve compared to the old way of doing things? Well, the impact is frankly stunning.
The results are just staggering. Look at this comparison. The old way could take up to 40 weeks to get a replacement part. The new way? 5 days. The potential cost of downtime the old way could climb past $500,000. The total cost of this high-tech repair? Less than $2,400. This isn't just an improvement, it's a complete revolution in repair.
And the implications here go so much further than just this one water company. As the team pointed out, this whole case study proves that the technology is ready right now. It's available to help all kinds of industries that rely on this critical, aging infrastructure. We're talking energy, transport, manufacturing, you name it.
And that leaves us with a really fascinating thought. For decades, when a part like this became obsolete, that was just the end of the line. This technology changes all of that. So if we can digitally resurrect pieces of the past to keep our present world running, it really makes you wonder, what can't we fix?